And let's talk about, of course, what you've done and where we're headed as we get here towards the end. As you know, the last time we were together, you took an exam, and I hope it went well for you. They're still sitting in a box in my office there, and so I haven't got a chance to look at them, but that is my plan soon, and hopefully even before Friday, but usually with my schedule, usually Friday. So I'll get on them on Friday, and between Friday, Saturday, and Sunday, I should get them all graded and pass them back to you on Monday. That's the game plan. Added to that game plan then is, as you know, we got finished with chapter 12 and just took the test on it, so we're about to begin 13. And so we have 3 more lectures left this semester, and I'm going to cover, to the best of our abilities, chapters 13 and 14. So the idea is that we will spend a day and a half on 13 and a day and a half on 14. But at the same time, I'd like to get the test back and go over them. And of course, at the same time, I was so busy with the remodel plans that we... and other things, that we canceled the lab, as you know, on Monday. And so we have one more lab, and I was deciding on which of the 2 to do. Should we do the one we skipped, or should we do the one that is scheduled? And so looking at it, I decided it would make the most sense, I think to be the most benefit, if we just completely skip the one that we did not do this week, which had to do more with chapter 12 that you just took the test on, than the new material, which is Archimedes' principle. And so next week's lab on Archimedes' principle, we're going to do the Archimedes. A couple of you were asking, okay, which one are we doing next week? And that's the answer. We're going to do the one that is scheduled. It's the Archimedes one. The reason, or another reason for that, is because the Archimedes one is not a very long lab. And so what I want to tie together with that is a chance to go over the exam if you so choose to want to go over the exam. So I will pass back the tests in Monday in class, but not go over them. I'll pass out a solution, or I might even just email you to save some money and some paper, and so you can have the solutions. So then on Monday, what we'll do is we will go over we will keep talking about chapter 13 and into 14, and then we will go into lab, and we will do the lab, and anybody who then wants to hang around and go over the test, we will take that opportunity to go over the test. So that's our plan. So in lecture 13 and 14, these next 3 lectures. In lab, we will do Archimedes' principle plus a review of the test for those of you who'd be interested in going over the test, which I think there will be a number of you, and that's why I wanted to throw that opportunity. So I think that's the best use of our time. So with that said, then, let's begin. And probably the best way to begin is to say we're going to this next chapter, 13. The good news is you have a chance maybe to lift up your right hand, put it over your left shoulder, and say, I got through the hard stuff, right? I did chapters 9 and 10. And so I've been telling you for a while that 9, 10, and 11 and 12 are hard stuff. But 9 and 10 in particular, because not only are they, particularly 10, on new stuff in terms of rotation, and it has that moment of inertia, but it is some long chapters. So I think you probably noticed that the material seemed harder than the one before, and of course test 2 I think seemed harder than test 1. And now we get into a few more things to wrap up, and then the final exam. In fact, maybe I should mention your final exam while we're here. I was going to wait till next week, but maybe I should just start now. And for the next 3 days, or 3 times that I see you in lecture, here's your final exam. It'll be 6 or 7 questions. Haven't really decided for sure which one it is. But for sure of them, there will be 1 problem from chapter 13 we're about to cover, and there will be 1 problem from chapter 14, which we are about to cover. So we obviously just have these little pieces. We don't have a whole test on it, but you can guarantee 2 of them. 1 will be from 13 and 1 will be from 14. So that's the game plan to get you to do the homework and to study and learn the material on these last 2 chapters. Oh, and maybe I should mention the test day. I better check myself. I'm pretty sure you guys are on Wednesday, right? Yeah, so if you don't already know, during finals week, your final is scheduled for 1 day during the week. Even though your class is 2 days a week, you only go to your final one time. You don't have two finals. So you don't have a final on Monday. Yours is on Wednesday. And so whatever final you have on Monday, go to that one, which they usually alternate. So if you, I don't know if anybody has a class right after this class, but if you do, that is probably on the Monday. They tend to alternate them so that if you have two classes back to back, they're on different test days. Of course, that also means then if you have a class, a gap, and a class, then those two end up on the same day. So you can easily have that. All right, well, with all that said, then let's go ahead and talk about this chapter. And it can be summarized and really quite simply said, it is one new piece of information. Now, the consequences of that are quite dramatic. So we're going to see some pretty challenging problems, not like you've been doing, but reasonably challenging problems. But the idea of the chapter, and the reason why I call this a fairly easy chapter, is there's just one idea. Now, it's a main idea, but it's just one. So let me get it across first. It's called the universal law of gravity. It was discovered by Newton, so sometimes we call it Newton's law of gravitation. Okay. But it simply says this, that if you have two objects, they will interact, they will pull on each other because of gravity. All right. In other words, if you have an object of mass m1 and another object of m2, they are attracted together. Well, most people realize that when they think about, say, the sun and the earth, or the earth and the moon, or even the earth and a marker. Gravity pulls on it. And after quite a bit of analysis, Newton came up with this, that the force of gravity between two objects, and he puts it in words, as directly proportional to the product of the masses. Okay, so the force depends on both masses, directly proportional to the product, and inversely proportional to the distance squared. And so the R in this diagram is trying to show the distance between, and let me emphasize, the distance between their centers. And so we'll go from center to center, all right, and then this will be the force between them. So notice the force depends on each of the masses and how much distance is between them. Now, since he said they are proportional, that means to make it an equation, there must be a proportionality constant. There must be some number that connects this mass and distance with force. And of course that number would depend on what units you are using. We like to use the unit of newtons for force. So this constant, which we will call the universal gravitational constant. Notice it's a big G, not a little g, right? Remember the little g we've used for the acceleration due to gravity. This is not the acceleration due to gravity, although obviously it must be connected to it. But this is the gravitational constant. And to make the units work out right, it must be measured in newtons for force, and meters for distance, and kilograms for mass. And so you can see if you put those units in front of here, the meters in this would cancel with that, the kilograms in this would cancel with the kilograms we get from that, and you would be left in a unit of Newton for the overall force. And it is 6.67 times 10 to the negative 11. And so that is the gravitational constant. And so in this beginning step, and I might point out the main step here of this chapter is to say that the force of gravity can easily be calculated just by knowing the masses and the distance. Let me also point out something very clear. The reason we use this word universal, because this is the same equation for any set of objects. So if you're trying to figure out the force of gravity between the sun and the moon, you would use this calculation. But if you want to do the Earth and this lead sphere, you would use the same equation. And maybe better still, if you wanted to know the force between these two lead spheres. Did you catch that? It's not something magical about planets. It's not just that planets and stars and suns have gravity. Everything has the force of gravity. And so if you wanted to know the attractional force between these two, you would again use this same equation. That's part of the reason why this is such a short chapter. It's universal. It applies for everything. So we don't have to really care whether we're talking about the Earth attracting the moon, which is really what we often think about in terms of gravitational forces. But this could be as simple as one rock attracted to another rock. Or if you're feeling confident, you could say you would be talking about how everything else is attracted to you because of the gravitational force. And if you really want to push it, you could say I'm going to eat more cheeseburgers and fries because the more massive I become, the more attractive I become. And so better still, right? But the idea here is me just kind of stopping and camping for a moment and saying, this is the main piece. If you learn that, there is nothing in this chapter that you can't do. It's been a while since I said it, and we've been dealing with harder material, so it's kind of nice to see that, again, physics is about knowing how to apply a few powerful, fundamental concepts to explain a universal phenomenon. And so everything about gravity, whether it be how the asteroids interact with the sun, or maybe how a meteorite crashes into the Earth and pieces fly and some fly away off of the Earth, or maybe Mars is a good one since we often hope for that they'll fly off of Mars and then eventually get caught by our gravity and then fall to Earth, and so we can have little Martian rocks that we can study without having to go to Mars. And so whether we are talking about Mars or the Earth or two lead spheres up here on the desk, it's that same general principle. And so it's been a while since I've said this joke, but maybe it's worth repeating. Would you like to know the answers to all the homework problems for this? Well, you're going to get it anyways. There it is, right? That is the answer to everything that we're going to cover in the chapter. Now, we are going to then look at that in great detail. And we're going to see some things you haven't done before. And yes, there's going to be some calculus involved along the way. But that is the main idea. So let's do this. Why don't we start our calculation by simply taking where we are probably the most familiar with when it comes to gravity. How about the Earth and some object? And so throughout this semester, we've been doing this a lot. We'll say, okay, look, you take an object up here, you hold it, you let it go, right? It falls. So this I will call mass of Earth. And I'll use the E for Earth, but since it's a big object, I'm going to change it to a capital M, okay? And then over here, I have whatever object is in my hand. Let's call that the second object. So that's going to fit into this equation as M2. All right, so I'll put a little m since this is not nearly as big as the Earth. But whether I'm using a big M or a little m, I don't really care at this point. It's just this is how I would calculate it. So doing our first calculation, I would say, what is then, according to this universal law of gravity, what is the force on this object? Well, of course, there's a couple things you'll need to know and able to answer this. The first one is, what is the mass of that object? Well, it's 1.5 kilograms. I'm going to tell it to you. Of course, the other big one is, what is the mass of the Earth, the other object? So it is 5.98 times 10 to the 24th kilograms. In fact, it's probably a good time to point out that in one of your covers, I think it's front here, yes, they list all kinds of information about all the planets. We can debate if Pluto's a planet, I suppose, here. Is Pluto a planet?
Yes, yeah.
Okay, but whether you accept Pluto as a planet or a planetoid now, we have it listed here along with the other 8 planets and along with the moon and along with the sun and their distance and their radii. So we're going to need that chart probably a lot here to answer a lot of these questions. Of course, Google's just as good too, and you can just type something in and pipes up quicker, especially if you don't have your book nearby. But that being said here, we've got the mass of the Earth, we've got the mass of the object. Now we need the distance between them. Now, what would be the distance between them?
The diameter. I mean, twice the radius.
Okay, so I want you to certainly notice that the distance between them is not just the distance above the ground. That's kind of the big thing here. So coming back to this universal law of gravity, what the distance between them is from their center to the center. Now, the distance between the surface and the center of this little object is not that much. Maybe 3 to 4 centimeters, not a big deal. But the distance to the center of the Earth is a big deal and is a big number. So again, looking back on this table there, I will see that this radius, which let me label as radius of the Earth, is 6.37 million meters. And so it's a huge distance. In fact, it is such a large distance, I should probably even ask, do you really care about maybe this 1 meter that is above the ground? In other words, if I start to write out what is the force, and I put the 6.67 times 10 to the negative 11, for the constant, and then I put the mass of the first one, 5.98 times 10 to the 24, and maybe I should put units in here the first time, and the mass of the other one, and divide that by the distance between them squared, 6.37 million meters. Should I add 1 meter to it? And good, it looks like you guys are seeing that adding 1 meter or not adding 1 meter really isn't going to change much. In fact, looking carefully at this equation, hopefully it will help us understand a little bit more of what we were doing, because what we are doing now is an extension of what we were already doing. I mean, didn't we already talk about the force of gravity, the weight of an object? I mean, hadn't we been doing that? Before we started this chapter, I'll come over here, how did we calculate and define the weight of an object? Wasn't this it? And so didn't we say that if I was calculating, say, the weight of this object up here, I would do something like this. I would say 1.5 kilograms times 9.8 meters per second squared, right? And one thing that we said is we didn't say how high was it above the ground. Did it really matter if we were to ask what is the weight when it is up here on the table versus what is the weight when it's down there on the ground? Didn't we say it's the same number? And so now I'm trying to give you a little more insight that it's technically not quite the same number. But when you have 6 million and you add 1 to it, it's really not going to change, certainly within 2 decimal places. So we ignore it. And so this, what we had been doing, is an approximation of this. And then, don't get me wrong, it's a good approximation, because adding 1, like I said, is only 1 part in a million. And so you're not going to notice it. And I'm sure you the same way. I'm sure when you sit on the floor and when you sit on a table, you're not going to say, hey, I'm lighter on the table. I am further away from the earth. My weight is a little bit less. And I guess technically, if you were to say that, you are right, but it's not going to be a measurable amount. You probably never even noticed it. In fact, I bet if you went higher, like the 2nd floor here, 3rd floor, 6th floor, I doubt if there's anybody in the world who ever went up to the 6th floor and said, you know what, I just feel so much lighter up here. I feel like I lost 5 pounds. It's just not that high. And in fact, what if I were to take this object and go to the top of Mount Everest, tallest mountain in the world? Is that high enough to even be noticed? I guess I need to do some unit conversion, because I do not know how high Everest is in meters. But in feet, it's 20, or before the earthquake. Actually, nobody that I know of, they're still doing rescue missions over there. But I think somebody's going to come back and say Mount Everest is 8 inches taller than it was before the earthquake, or some number. I'm just guessing on, but it wouldn't surprise me if it is 8 inches or a foot higher than it was before. It was a good-sized earthquake. Anyways, and Mount Everest is very tall because of all the land crashing together over there and pushing it up. So having big earthquakes over there is not a surprise, and that's why it's 29,000 feet. But going up to the top of Mount Everest, 29 feet, divided by 5,280 feet, that's how many miles, times 1,609 meters, gives me, to the top of Mount Everest, 8,846 meters. Oh, I forgot my million. Meters. Will it weigh less on the top of Mount Everest? And we're back to the same discussion. Technically, the answer is yes, it weighs less. But let's get some numbers. And you'll see that even to the top of Mount Everest is small compared to the radius of the Earth. And so if I get out my calculator here, and maybe I'll do this calculation first, 6.37 million plus 1, and square it. So I have a big number, which I will put downstairs in just a second. So on the top, 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 times 1.5 divided by that last answer gives me a force of about 14.7 newtons to 3 significant figures. Okay. How much does that same object weigh on the top of Mount Everest? All right, well, let me do the denominator first. 6.37 million. Add to that 8846 square that, or I'll save that for the end. Now I'm going to go to the top again. 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 times 1.5, and all of that divided by my last answer gives me 14.7 newtons. Okay, didn't change. Now, it looks like it did change. I didn't write out the next decimal place because it wouldn't be fair because I don't know it, but the last decimal place was a little different. And so if I were to maybe look up the radius a little bit better, look up the gravitational constant a little bit better, look up the mass a little bit better, weigh this, we'll say that that's 3 significant figures, a little bit better. Maybe then Mount Everest would be high enough that there would be now a noticeable difference. My point is that we, by doing this calculation, which by the way comes out to be 14.7 newtons, gives us the same number essentially everywhere across the surface of the Earth. And so that's why we had, although now we're trying to say a little bit incorrectly, had said that the force of gravity is always a constant. It is not. It does change with height. But the height has to be really high. And so our general rule is, especially as you come up to the final, if there is a problem involving, say, a roller coaster, and you need to use the force of gravity either to get the acceleration or the force of gravity to get the potential energy, use this. That's fine. That's the way we learned it. We're going to keep doing that. But on the other hand, if there's a problem on the final or a problem in the homework that has something going out of the atmosphere, don't use this. And so we'll just kind of let that be our boundary zone, the Earth's atmosphere. Anything in the Earth's atmosphere, we'll say, this is its weight, this is the force from gravity, this is a simpler calculation than this one. This one does not change with height. Dealing with the energies and accelerations are much easier when things are constant. And since this is nearly a constant, we can then use this as approximation. Fair enough? And so that's what I want to start off by saying. We have been doing that. We've been doing an approximation. And now we're going to extend that. And so you'll see the problems we're about to do will usually involve problems outside of the Earth's atmosphere. So that we can say, hey, we are beyond the height where this number now does matter how high we are. Right? And so how high we are becomes an important discussion here. And so that's the first thing I wanted to point out, is that we have been essentially doing the same thing. Now also in here, I don't know if you caught this, but doesn't this explain something more? I mean, it doesn't just explain why we've been treating the force of gravity as a constant, but it also explains the 9.8, doesn't it? Where does the 9.8 come from? Now, maybe I should say we got the 9.8 because we just did a lab on it the very first week, and was that the first? Yeah, the first week we dropped Bob. We did Falling Bob, and we measured the acceleration due to gravity. We said it was 9.8. We did not give you an explanation of why it was 9.8. We just said it was 9.8. Would it be 9.8 on the moon? No. Could you find it on the moon? And I hope you can. That's what the new lesson is. Where does this 9.8 come from? Do you see that must come out to be 9.8 then? And so the reason we get a 9.8 here on the surface of the Earth is because of the mass of the Earth and then the radius of the Earth. And of course, if you were on the moon, would you get that? No. And so the acceleration, which we call the acceleration due to gravity, is the force from gravity divided by the mass of that object. So in this case, it would then come out to be g mass of the Earth divided by the radius of the Earth squared. And there's our 9.8. If I wanted then to know what is g on the moon, could I figure it out? What would I need to know?
Radius.
Yeah. And so the universal gravitational constant's the same, but I would need to know now the mass of the moon and the radius of the moon, which is fortunately in this chart. So the mass of the moon is 7.36 times 10 to the 22. So 736 times 10 to the 22. There's the mass of the Earth. What is the radius? I'm not the Earth, the moon. What's the radius? 1.74 million meters. And maybe I should also include my units here. But I think you will see that once you do, you will get the meters to cancel off with meters and one of the kilograms to cancel off, not both, since we're not doing force, we're doing acceleration. And a Newton divided by a kilogram is a meter per second squared. So this up here would have come out to be units of meters per second squared. As we know, it should. It's an acceleration. And this one's getting kind of dry. Maybe I'll... oh, I don't have any blue. That's not good. I'll go to green. I forgot to check my colors here. Actually, I wonder if there's any up here. Yeah, I'll do that one till it dies. All right. So then I can get the acceleration of an object on the moon. And I could do it on Mars. I could do it on Jupiter. I could do it on the sun. I could do it anywhere that we need it here. And just working with the moon here, 6.67 times 10 to the negative 11 times 7.36 times 10 to the 22 divided by 1.74 times 10 to the 6th squared comes up to be an acceleration of 1.6. I'll go one more significant figure, 1.62, which maybe you even heard a phrase we like to use a lot, that the moon is 1/6 of what it is on Earth. And so we see that the causes, which is the mass of the moon and the radius of the moon, change things. And so now we could do any planet that we want. And you'll be asked to. You'll be asked to figure out what's the acceleration on the surface of. Yeah.
How did Newton measure the masses of any objects?
Ah, very good question. Now, the mass of, say, the Earth, you just put it on a scale, right, is obviously tough to get, and Newton never knew it. In fact, the only masses that Newton actually knew were the ones, locally, because you put it on a scale. And so I was joking, but that's all he had the technology to do. He could say, this is our definition of a kilogram, and so you put something on there and then put equal, and ones you already know, and then you compare them. So that's all he was able to do. So today, and I think it's your question then, is how do we get the mass of the Earth? I will in just a second show you that. And the way we get it for the Earth is how we get it for the other planets and the sun. So you'll, I think, appreciate that, but Newton never did. Also, even going one step further, Newton actually never knew this constant.
You say it was a constant?
Yeah, he just knew it must be proportional. So coming back to our phrase here, he wrote this down saying it's got to be proportional to it. But since he only knew masses that were small, the best he could do is to take, like in this experiment, two small masses And he could even make them bigger, but compared to the Earth, they were still small. And then try to measure the force between them. And the force was so small, he was never able to do that. And so he was never able to get G. It was Cavendish, and there's a famous experiment, and your author refers to it about it. And it's why in England, there, I think it's at Cambridge University, where you have the Cavendish laboratories named after Cavendish. And then he finally figured out, and this was close to 200 years later after Newton, but he was able to do a very clever experiment that was allowing him to measure the force between two lead spheres like this. And really quite clever. Roughly it goes something like this. He took a lead sphere and another lead sphere, and he balanced them. So say I'm the balance, and they kind of hold like this. And then this was all hanging from a thread. Now it had to be a strong thread to hold this weight, but nonetheless it was as thin as he could make it, a wire thread going up. And so it would be like this. And then he realized that if he brought in another object near it, there would be a gravitational force, and this would turn. Now, not by much, because you're twisting the thread and it's getting tight. So it's going to turn just ever so slightly. But he realized then that this force between them would be small, but so is the torque you get from twisting a thread. And when he first tried it, it didn't look like it moved. And he's all, oh, bummer. But then he had a very clever thought, is he then, on this balance, mounted a mirror, and he took the sunlight in from the window on the mirror and projected it on the back of the laboratory. So in this case, 40 feet away. And so now if there's a small twist, you'll see that little beam of light move. And so that beam of light would amplify the motion of the twist. And so he was able to figure out that because of it. So yeah, very, very clever experiment. So anyway, the first time in history, somebody was actually able to find that number. And once you find that number, that's going to open the door to finding other numbers, including the mass of the Earth and the mass of the Moon and the mass of. So I'll get back to the mass of the Earth and how we get it here in just a second, because that's a good discussion showing you this in operation. But I think you get my first main point. And that's my first main point is this is the new principle. Everything we do today and then half of Monday is all based on this, everything in this chapter. And I just wanted you to see how we are treating it and how we've been treating it are not in conflict with each other. They are really the same thing. Okay? And now we've just opened the door that we can find the acceleration not just here on Earth, but actually then figure out what it should be on these other planets, even though we're not there. We don't have to go there and drop Bob to get the acceleration. And obviously, when you were sending men to the moon in the 60s here, it was important to know what the acceleration on the moon was, so that then you can leave the moon and return back with whomever is walking on the moon. And of course, if you're going to walk on there, the other thing is if it's too low, that could be dangerous. Could it be too low such that somebody could actually jump and float away? And of course, as you know, the moon is not that low on gravity. It's 1/6. So, you know, you jump and you go, hey, I can jump a foot in the air, yay. I mean, on the moon, I'm probably jumping 6 feet. Now, that's pretty nice. 6 feet, coming down 6 feet, much longer time. Well, anyways, I better move on because I don't need to do all the planets, but you never know what shows up on the homework or the test. Which planet are you supposed to calculate? Let's add to this. What if I had something like this? What if I had, say, object 1 here, and object 2 was, say, here. let's just say it is R1 away. But then I had another object, object number 3, and let's just say it is R2 away. How much force is on object 1? What would you do here? Now there's more than 2 objects. There's 3 objects, or 4 objects, or 5 objects. How are you going to handle this one? Well, I hope you see that there would be a force from number 2 on number 1 that we could calculate using the universal law of gravity. But likewise, there would be a force from number 3 on number 1 that would also then I could calculate using the universal law of gravity. And then to get the total force, I would have to combine them together. And so use the idea of summation of forces that we learned way back in chapter 5 to figure out what the net force is. So I guess it would look something like this, that I would say, all right, force 2, 1 with a vector would be G M1 M2 separating by a distance of R1 squared. That would be its magnitude. But its direction then would be in the negative J hat direction. Fair enough? And so there is the force of gravity on number 1 from number 2. And of course, what would be the force of gravity coming from number 3 but on number 1? Well, again, this would be G, and we would put in the M1, but this time we'd put in the M3, and the distance between them would be R squared. So there is our universal law of gravity. There's the force from the third object. What direction is it? Plus I hat direction, right? Oh, we could even extend this one more step. What if there was object number 4? Well, then I guess object number 4 would be some distance away, which if I kind of center this up to be a rectangle, then the force from number 4 on number 1 would be an R1 squared plus an R2 squared. Wouldn't that be the distance squared from them using Pythagorean's theorem? And so that must be the distance away. The numerator would be G M1 M4 here. But what direction is the force? Right, wouldn't we have components? So maybe I should label this as theta. Wouldn't, to get the x component, you would go cosine of theta to get the I hat direction? And let me just put a little parentheses there, because it would be the magnitude times the cosine of the angle. How would you get the vertical component? Yeah, good. Same idea. And so, again, I think you guys are getting the idea. This is, again, nothing new here. It is just taking the universal law of gravity, applying it to each object, and applying the idea of the direction of forces and the components and putting them together. So this would be a sign. Now, let me be careful. It would be in the downward direction. In fact, I might even go one step further. Cosine of the angle would be R2 over R1 squared plus R2 squared square root, right? Isn't that what the cosine of the angle means? The adjacent distance over the hypotenuse. And sine would be r1 over the hypotenuse. And the hypotenuse would be the distance along the diagonal. And so knowing r1 and r2, I would also know not only the distance between 1 and 4, but also the angle or the cosine of the angle that's associated with it. And so I can put all those together. And that's my point number 2, is that this universal law of gravity can extend from beyond just 2 objects to any multiple number of objects that the problem requires, including adding an infinite number of objects, which I guess would be the calculus problem. What if you had a long rod? And probably in the interest of time, I guess I won't write out the calculus of it. We did a lot of that on the moment of inertia, and your author doesn't dwell too much on there. But that's this whole idea. Now, as I said, there's nothing that I'm going to do today that is anything different than just taking this universal law of gravity and applying it together with our past chapters, which is actually one of the main reasons I really like where this chapter shows up. It's 13, we're near the end. We know a final exam is coming up in 2 weeks, right? Wednesday of 2 weeks. And so I know you started reviewing yesterday, getting ready for your final exam. I'm sure you're not too busy to be worrying about more tests. And so as you are reviewing, let's use this chapter as an opportunity to review. And that's one of them. This is our chapter 5. This is adding net forces together. But let's now take this and talk about, say, the motion of the Earth around the sun. I mean, first of all, going all the way back to chapter 6, that's the first time we did circular motion. And when we did circular motion, we said, first of all, does an object that go in a circle, so here's the Earth, going in what I'll call a near circle. We'll talk more about the fact that it's not a perfect circle, it's an ellipse in just a second. But it's going in a near circle. Let me just call it a circle for now. And so as the Earth goes around in a circle, is it accelerating? You remember that discussion in chapter 6? Why would you say it's accelerating?
Changing direction.
Changes direction, right? Our definition of acceleration was, and still is, a change in velocity. And velocity is a change in speed or a change in direction. And so I'm not saying that the Earth changes its speed. And if it was a perfect circle, it wouldn't change its speed. It's not quite a perfect circle, so it slightly changes its speed. But if it were to go around in a perfect circle, it would not change its speed. But does it change direction? Yes. So does it have an acceleration? Yes. And what would be the formula for that acceleration? And yes, we worked this out in chapter 4 and extended it into chapter 6, and it's a good review now.
B squared over R.
Right, it was the centripetal acceleration. We said that if an object is going in a circle, and so at first we called it centripetal acceleration in chapter 4. Then we called it the radial acceleration in chapter 6. But we went through some geometry to say that the numerical value of the acceleration would be v squared over r, right? In chapter 5, we said Newton's second law was this: that the net force on an object is equal to its mass times the acceleration of the object. So taking those chapters, 4, which gave me this, and 5, which gave me this, and putting them together in chapter 6, we found out that the net force on an object in the radial direction as it goes around in a circle was mv squared over r. That all look familiar? Good. Right? And so, like I said, good chance to review. We did a lot of this in chapter 5. Nice review. We did this logic here. But now I want to incorporate it to what we are talking about here, because that means this mv squared over r is the centripetal acceleration. It comes from the sum of all the forces. Let's look at the Earth going around the sun. Let's add up all the forces. What forces are on the Earth? Exactly, there's just one. It's a force of gravity coming from the sun. And I guess ignoring the other planets. Okay? The sun is just so much bigger than the other ones. So that means this must equal to capital G m1 m2 over r squared. That's what I meant by, let's just take what we've been doing, and this is what we've been doing, and put it together with what I'm trying to say now. And so we have what some of you might have already learned, Kepler's third law. And Kepler noticed this pattern before Newton really came up with, well, Kepler was before Newton anyways. But we are going to then, I guess, prove Kepler's observation. That there's a relationship between these factors. Now we got a little bit more work to do to get to Kepler's third law, but his observations nonetheless are carried out here by Newton in his universal law of gravity. Now, I'll keep going. This r coming from here is the radius of the circle it's going around. What's this r?
Is between the two objects.
The distance between them. So, aren't they the same in this case? So, I'm going to go ahead and cancel an r on this side with that side. So, there's still one r left over here. Oh, what about this m? What's this m? And what are these m's? Well, these are the two objects. In this case, we're talking about the sun and the earth. Maybe I should put then an S under this one and an E under that one to remind me, okay, one of them is for the sun and the other one is for the earth. It doesn't matter which order I put them in, mathematically they're the same, but one is for the sun and one is for the earth. But what's this M? That's the one going around in the circle, so that would be the earth. Okay. Now it's important to recognize which one it is, because can't I cancel? And so the one over here cancels with the one over there. But again, want to make it hopefully very clear which one I'm allowed to cancel. I'm canceling the one that goes around, whereas the bigger one still remains in the equation. Okay. And so what I have so far is a velocity squared is equal to g times the mass of the sun divided by the radius, right? If I knew the velocity of the earth and I knew the distance from the earth to the sun, then I could answer your question earlier. Could we find the mass of the unknown, which is the sun? And so this is set up perfect to find the mass of the sun. Now, granted, I'm going to need to know the speed of the earth, but I think I can get that fairly easy. Wouldn't the speed of the earth be the distance it travels? So there's a circle, 2 pi r, and the time it takes. Let me use capital T to represent the time it would take to go all the way around. So if I square this, I get velocity squared equals 4 pi squared radius squared over period squared. And it's too bad I ran out of space on that side of the board. I'll come over here and finish that calculation, but then I also want to come back and get some other pieces of information. But if I put those two ideas together, then I get 4 pi squared r squared over period squared, so that's the velocity squared, equals to g mass of the sun r. And if I rearrange this so that all the r's are together, and I rearrange it so there's no fraction, we get what Kepler noticed. Kepler noticed that the time it takes for each of the planets to go around, squared, is directly proportional to the cube of their distance. And so some of you, I know, have come from an astronomy background, and so you probably have learned Kepler's observation. Yeah?
Where did the mass of the sun go when you went from?
Oh, crap. No, I forgot the mass of the sun. I forgot the square there also. Okay. Mass of sun, sorry. Period squared. Thank you. All right. So, I'll say it again. There is a direct correlation between the square of the time it takes to go around and the cube of the distance. And so, at least from a physics point of view, poor Kepler, we don't even pay much attention to it anymore. It was a great discovery, a great observation, but it doesn't explain why. But Newton does. Newton makes it very clear. And so I could just start with Newton's universal law of gravity right here, together with my mechanics, put it together, and come up with Kepler's law here. And I wanted to do this because you had asked the question earlier, then how did Newton get the masses of them? And of course, as I said, he did not, because he did not have this information. But we do. So let's put this in here. If we know, say, the distance to the sun and the time it takes to go around, we should be able to get then the mass of the sun. And so I'll put in the 4 pi squared. Now, the distance to the sun, of course, you would have to measure. We know that number. It's 93 million miles. I believe that's 1.5 times 10 to the 11 meters. I should double check this. Average distance between the Earth and the sun, 1.50 times 10 to the 11. All right. So there is the distance between the two objects, which in this case is the sun and the Earth. The g, as we mentioned earlier, was that magical point that if you can find out g, now you can get the mass of the sun. Or the other way around, if we knew the mass of the sun, we could get g, but we didn't know that. And so getting g was Cavendish's goal here. I'll put in the units. It's Newton meters squared, kilograms squared. So there's the value of g. I would like to find then the mass of the sun. And then the period. How much time does it take to go all the way around? And I picked the Earth because I thought you would know that one. It takes 1 year, obviously, 365 days to go around. So 365. Actually, as a side note, is it exactly 365? Yeah, why do we have a leap year?
Because every 4 years.
Yeah, it takes a little bit longer to go around, and it's a little bit more than 365. It takes 365, and I heard somebody say a quarter, but actually maybe we should, how much time do we have? Well, we could expand on that. The quarter means that if this Earth goes all the way around, in 1 year it doesn't quite get back to the same spot. So the next year the same thing, the next year the same thing. After 4 years, what happens? You're backwards by 1 day, right? And so the sun, say the winter solstice, is no longer on December 21, right? It's back a day. And then if another 4 years, it's back another day. Another day. And before you know it, the middle of winter is in September. And then August. So the whole reason we have a leap day is to add it. However, I'll do you one better. It's not exactly a quarter.
So are we eventually just going to skip the leap day?
And
1 year is going to be like, oh,
maybe I'll go quickly with this. But think of this as 365 plus a quarter minus 100th. Let's talk about that for a moment. A quarter minus 100th. Isn't that 0.24? See, a quarter is 0.25, and then 100th would make it 24. Fair enough? Okay. Plus 1/4 of 100th. Isn't that 0.0025? A quarter of 100th? Yes? Okay. Minus 3 10,000ths. Fair enough? So here's our calendar. Most people know the simple part of our calendar, and that is 365 days. Most other people know it is one extra day every 4 years. That's plus a quarter. Not many are aware of this. What's this? No leap year every 100 years. And so every 100 years, we do not have a leap year.
When's the next time that's going to happen?
So let's talk about our calendar. This was first imposed in 1600, and in 1600, although it is a multiple of 4, there was no leap day. There was no February 29th. And every 4 years there was, until the year 1700. And in 1700, there was no February 29th. So you put in a February 29th every 4 years, but you take it away every 100 years. And so it made sense to do it on the century mark. So February 29th here, but no February 29th in 1800. Then a February 29th every 4 years, but no February 29th in 1900. Then we get to 2000. The year we were alive. Was there a February 29th? It was a special February 29th. Why? For the first time in the history of our modern calendar, we added back the leap year day on the century mark that we have been taking away every century, and we put it back in. And fortunately, most people never caught that. It was just, February 29th, every 4 years. We have a leap day. But it was a big leap day. It was the first time that we added it back in. And of course, we just went on our merry way, thinking, February. And so, should any of you be so fortunate to be alive in 2100, there will not be a February 29th in that one. Should any of you be so fortunate to be around in 2400, there will be a February 29th. Although we'll take it away in 3,333 years for anybody who's around in 3,333 years. So, important little subtlety there. Anyways, I got sidetracked there. So let me put the time to go around as 365, and I'm just going to put a quarter. I'm not going to go do the 24, 22 there. But that's how many days it takes to go around. As you know, there are 24 hours in a day. And as you know, there are 3,600 seconds in an hour. And so I will square that. And so being careful with my units, this being in seconds, this being in newtons, meters, and kilograms squared, this being in meters squared, all of those cancel, and I will then get my units in kilograms. And so using the motion of the objects going around is what I'm trying to get at. We can figure out the mass of this. And it makes sense, because isn't the object going around, its motion is dependent on the mass of the object forcing it to go around, which in this case is the sun. So this is a great way to get the mass of the sun. Notice we can't get the mass of the Earth. Yes, there is a force on it, but its force is influenced by its own mass, as well as its acceleration is influenced by its own inertia. And the two cancel off. And so whatever planet is at this particular location, whether it be a heavy planet or a light planet, it cancels off in all the equations. So we're not going to be able to get the mass of Earth this way, but we can get it for the sun. Yeah.
Yeah. Don't the other planets like affect it too? So does that give us like, I'm not sure how to ask this, but like, don't the other planets goof this up? Because it's not just the sun and the Earth, it's not just the sun's gravitation that's affecting Earth. Like,
right.
Isn't there Jupiter's too, even though it's way out there?
Yeah, there's Jupiter, and Jupiter keeps moving. And so as you factor that in, yes, that does. In fact, over a long period of time, and I don't know if 3,000 years is enough period of time, but I know after a long period of time, it fouls it up so much that even just this little bit of foul up over millennium, we don't know where the Earth is going to be. And so it's a good example of what we call chaos theory. And to ask somebody at NASA, where is Earth going to be in, and like I said, I don't know if 3,000 years is enough versus a million years. I'll just pick on a million years. But there is a time period that they would have to honestly say, we have no clue where Earth is going to be. Because a slight change that is equal to the, grain of sand now will have a dramatic compounding effect in a million years. And so we don't know if the Earth will be a planet going around where it is now, or if it'll be closer in, or if it'll get pushed further out, or if it'll be what they call these rogue planets, where they get pushed out of their whole solar system. And so, that's a big question in astronomy. How many rogue planets are out there? We know that when solar systems are formed, they make a lot of rogue planets. But being floating around in outer space with no sun nearby, we can't see them or detect them in any way yet. And so we don't know how many rogue planets. And so who knows? The Earth may become a rogue planet.
I guess what I'm saying though is that, wouldn't that goof up our thing for finding out the mass of the sun? Or is it just to look at it on such a small time scale?
Yeah, it's a small time scale. Okay. And this is a time scale of 1 year. We know the period really well within 1 year. Yours is more of a long time frame out there. So grabbing my calculator, I'm kind of curious now, then what is the mass of the sun here? So over here, I will take the 4, multiply it by the pi. Whoops, that's not the pi I want. Let's try that again. 4 times the pi squared times 1.5 times 10 to the 11th, and I will cube it. Take all of that and divide it by 6.67 times 10 to the negative 11. Divide all that by, let me put in parentheses, 365 and a quarter times 24 times 3600, close and square, and I get a mass of 2.0 times the 30th kilograms. And so that should be the mass of the sun. And if I scan down in my little chart, yep, that's what they give me there for the mass of the sun. So not a surprise then that I get the same numbers in the book, because hopefully I did my physics right there. And so like I said, this was discovered by Kepler. It's Kepler's third law. And in fact, doesn't this step right here also then tell me what the speed of the orbiting object should be? And so let me continue with this discussion here, because this was nice that gave me the relationship between the period and the radius. In fact, maybe before I leave it, I should talk about the other planets. The other planets are nice to discuss, because if I make a list of the planets, so here's the sun. What is it? My very excellent mother just served us, thank you, us nachos. Used to be nachos and pizza, but I guess we're back to that same question. Do we include pizza or not? Most of you are saying we should include Pluto. Some of you are saying no way. All right, always a fun discussion. But it is, and actually I think that's a good point of showing how science evolves. I mean, we thought Pluto was the only thing out there, and then it turns out it's not. It looks more like Pluto, if you don't already know, has been demoted from a planet to a planetoid, because it basically has not pulled everything together. It's a planet unformed, and so it's a dwarf planet, and so they're going to form. It's going to be a planet in the future, but it just hasn't really made everything a planet, and so that's why our knowledge of science has evolved. I mean, we could take this all the way back. You know, we gave the word atom the name atom because we thought it was indivisible, right? And we know that's not true. We thought you couldn't break an atom apart, and now we can. We have things like a Brontosaurus. There's a good one. We found this fossil record, and we thought we had this dinosaur called Brontosaurus. The truth is, it was actually part of a body and part of another head, and they put it together and called Brontosaurus. And so the Flintstones got it all wrong. There is no Brontosaurus burgers, right? It's Brachiosaurus and whatever the other one is. And so they finally figured out these are really two dinosaurs. We used to think the world was flat. And I guess there's some people still think the world is flat. But those people outside of the discussion, well, we know the world is no longer flat. Anyway, so we have Pluto in that same category. But what I was getting at is that you can see in this equation that there's a mathematical correlation between period and distance. So clearly, the one that is closest in, Mercury, having the shortest distance, must also have the least amount of time to go around. If I remember right, this is like 88 days to go around. I bet it's listed here. No, it's listed in seconds. Well, without getting my calculator, I'm going to say it's 88 days. But that's how much time it takes to go all the way around. Of course, it's the whole reason it's given the name Mercury. Isn't Mercury the messenger god of the Roman Empire there, or the Roman gods? So, because it goes so quickly, and that's the whole idea. Venus, a little bit faster, 250 days. Earth, 365 days. So you can see that the ones that are inside, less radius, less period. The other ones then all must take more than 365 days. And as I scan down that chart, I can see them. I don't know what they are, but I do know or Pluto, which used to be a planet, is somewhere in the neighborhood of 250 years to go all the way around. And so again, it is at such a large radius that I think those numbers illustrate exactly what Kepler's third law is, exactly what our physics is trying to tell us, in the fact that we put together, and maybe again worth repeating, I'm doing nothing more here today than taking Newton's universal law of gravity together with the other stuff we have learned and learning something about, say, planetary motion or rocket motion or whatever the discussion leads us to. The other part I was about to get to is, wouldn't this then tell me the speed that the Earth would have to be traveling? And so we could put that number in here and say 6.67 times 10 to the negative 11. The mass of the sun we just figured out. And the distance away is the 1.5 times 10 to the 11th. And putting in my units, it's going to come out to be meters per second. And so this is the speed of the Earth. And so let me put in a couple of numbers here and take the square root of all of those numbers, and I get a speed, and I'm just going to round it up to 30,000 meters per second. And so you and I on the Earth are moving 30 kilometers every second. So if anybody ever invites you to do a 10K, say, I can do a 10K in a third of a second. No problem. Boom, did it. And so did everybody else, so I guess it's not that impressive. But there is our motion around the sun. That's our speed. And just to see that it works right, wouldn't we have done that what I would call the old-fashioned way, by saying distance divided by time? And so if I were to take the distance that the Earth travels around, that would be its total distance in 1 year. And so 365 and a quarter times 24 hours times 3,600 seconds better give me the same speed. And so let's see what I get. 2 times pi times 1.5 times 10 to the 11th divided by 365 and a quarter, and also include the 24 and also include the 36, and I get, not a surprise, 30,000 meters per second. However, I think more interesting than this can lead me to a different discussion. And this is where Newton wanted to go with this. He was trying to explain then why you do have orbits all together, as well as could we make an artificial orbit. Today, what we would call satellites. A more appropriate word is artificial satellites. Because all of these planets going around the sun are referred to as natural satellites of the sun. Natural because they were built by nature, not by humans, and they go around the sun. So they are natural satellites of the sun. If we change this whole derivation and look at the Earth with the moon going around, couldn't we repeat everything we've had? What would change here? Say in this one. Wouldn't I then have 4 pi squared r cubed equals to g mass of Earth and period squared? And so if I know the distance to the moon and the time it takes for the moon to go around, couldn't I then figure out what the mass of the Earth is? And let me not bother to calculate it. I don't think that's going to give you any insight. But it's exactly the same calculation where we can then find very easily the mass of any of our planets by looking at the objects that are orbiting them. So I started with the sun, but clearly using the distance to the moon, which in miles is about 240,000 miles, period is 29 days-ish. And if we look those up a little bit more accurately, we would get able to calculate the mass of the Earth. And yes, we would get that 5.98 times 10 to the 24 that I've been using since class started. And so there would be an easy way to get the mass of the Earth. I could do the same thing looking at the moons going around Jupiter and going around Saturn, and I'll get the mass of all the planets. And so that's where they came from. That answers your question earlier. How do we get the mass of them? And that's how. But I wanted to take this to the next discussion and go, instead of natural satellites, what about artificial satellites? Could I take the Earth and make a satellite that goes around here, but it's not nearly as far out as the moon? Sure, right? I could do that. Of course, looking back here at what I call Kepler's third law, wouldn't that say that if you're going to make it closer in, what does that say about the period? Yeah, much smaller. Oh, let's pick on, say, the International Space Station. 250, 300 miles up. Anybody know a more accurate number? No? I'll pick on 300 miles. I think that might be a little bit on the high side, but nonetheless, let's say it's 300 miles up. Okay. Using that, then I should be able to figure out its period. How much time does it take to go around? So 4 pi squared times r cubed is equal to this g times the mass of the Earth times the period squared. And so I'm going to change it here and figure out how much time would it take. What is the time frame for a whole orbit of the International Space Station to go around? Well, good. I heard somebody say about 90 minutes, so I hope I will get a number near 90 minutes. Let's see. Because I'll start here with what is the radius. Okay, so I think what you're saying here is if the International Space Station is 300 miles up.
249 if you're curious.
249? Ah, good. Let's go with 250. All right, good. And then we'll probably get closer to our 90 minutes that you hear a lot about. All right, so 250 miles. But clearly, it's not just 250 miles I put in that equation. Isn't it 250 miles and the radius of the Earth? You know, I heard somebody point out radius, but it's not this radius, right? This is the radius that the Earth is from the sun. But yes, it is the radius of the Earth, which we were working with a little while ago. That's the 6.37 million meters. Okay. And now let me go the 250 miles, but I also know there's 1,609 meters in each mile. So that will be in meters, and that will be in meters, and so now I can cube it. Okay, and so that's my distance there. This is the 6.67 times 10 to the negative 11. This is the mass of the Earth. And so now, after a little bit of calculator work here, I should be able to figure out how much time is it going to take for the International Space Station to go around. So 4 times pi squared times the quantity, 6.37 million, plus 250 times 1,609, closed quantity raised to a power of 3. So that would be this side of the equation. I'll go ahead and divide it by 6.67 times 10 to the negative 11, and then also dividing it by 5.98 times 10 to the 24, and then finally taking the square root of all of that gives me 5,544 seconds. So dividing that by 60 is 92.4 minutes. And so every 90 minutes or a little more, the International Space Station goes around and then I guess has a sunrise and a sunset. So sunrise and sunset every 45 minutes. All right. Yeah. And so, you know, as it circles around our planet. And so again, just the same idea. And the big one I wanted though is how fast does it have to go? Because that was really kind of Newton's question here. I mean, once Newton kind of figured out that this is how the planets move, and it's nothing more than the universal law of gravity plus the motion, he was saying, could we put up artificial ones? And of course, today we know we can. But what does its speed have to be? Well, remember what we just got earlier, that the speed would have to be the square root of gm that it's going around divided by its radius. And so just like our discussion for the natural satellites around the sun, we realize that these that are closer in must go a lot faster than these that are further out. And so our moon doesn't go very fast. It takes 29 days to go all the way around. But if we're going to put one here, then how much kinetic energy do we have to give it? How much speed do we have to give this satellite? And so this would be its speed. So in our case, it's the 6.67 times 10 to the negative 11. Mass of the Earth, 5.98 times 10 to the 24. Radius, now again, I guess we're back to this number here. It is not only the radius of the Earth, but the altitude which the space station is above. And so here's my 6 million and my 250 times 1,609 meters. But just out of curiosity, this is not a slow speed, which is why we need the invention of rockets before we can get our artificial satellites. And so Newton's idea was to put one up with a cannon. Now, you're not going to get these kind of speed with gunpowder and a cannonball here. But we obviously do get them with a rocket here. And so 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 divided by the quantity 6.37 million meters plus 250 times 1,609, taking the square root of all of that, gives me a speed of about 7,674. Probably shouldn't go that many significant figures, 0. Meters per second. So just a hair under 8,000. In fact, on the surface of the Earth, being a little bit closer than the International Space Station, it does come out to be a little bit closer than 8,000. And so we like to say, if you could take a baseball and throw it at 8,000 meters per second, what would happen? It would be pulled down. It would curve with the Earth. It would look something like this. If this is the curvature of the Earth, then this baseball that you throw is being pulled down let's just say it is 5 meters above the Earth's surface to start with. I pick the 5 meters. Maybe this is a good chance to review. If you drop the ball, how far would it fall in 1 second? So x minus x naught is equal to initial velocity times time plus 1/2 gt squared, right? So if you just drop the ball, doesn't it fall very near to 5 meters in 1 second? And it so happens that the Earth curves down, right, well, here, 5 meters, if you were to walk 8,000 meters that way. So if you were to go on a 8K run in a straight line, you would actually be 5 meters curved around the Earth. And so it's perfect that then if I go sideways 8,000 meters in 1 second, the ball will still drop its 5 meters, but it won't be any closer to the surface of the Earth. It will still be 5 meters away. And so it will make a clean orbit. You go a little bit higher, as we said, you don't have to go quite to 8,000 meters, but you're pretty darn close. And so this would be the speed of the International Space Station. Or for that matter, it would be the speed of anything placed in orbit 250 miles above the Earth. And so if this is a supply ship going on up to give supplies and take waste out of the International Space Station, you got to send it off and give it a speed that is the 7,000. Actually, you usually hear 17,000 miles an hour, so this must come out to be 17,000 miles an hour. And so that's roughly, in terms of miles per hour, what is the speed of the International Space Station? Fair enough? Well, we've done a lot of velocities and distances. Well, let's talk about energies while we're here. Maybe the easiest one is the kinetic energy. In fact, it's almost so easy I won't even bother to look up what is the mass of the International Space Station. But could I get the kinetic energy of the International Space Station? Yeah, I mean, how would I get it? Yeah. And so, again, it's a good chapter to review. In Chapter 7, we learned an equation for kinetic energy, didn't we? What was it? Or maybe I should say, what is it? Yeah, 1/2 mv squared. So in this case, it's 1/2 times the mass, which, I don't know, they list it there too? Oh, well, I don't want you to take too much effort to look it up or anything, but I don't think it's that important. But if we knew that mass, then we could put it in with the speed of the 7,600, what would I get there, and 70 meters per second, and I can square that, and I could get the speed in units of joules, right? But the real discussion I want to have is not so much about kinetic energy. How about potential energy? Gravitational potential energy. Didn't we learn that one also? I think that was Chapter 8 instead of Chapter 7. What was or is the equation for potential energy? Actually, I think we just used the symbol K, and then we used the U, G, and I heard people say it, MGY or MGH. Isn't that the equation for potential energy? Uh-oh. This one we need to rethink. Where did that come from? Didn't that come from integrating the force of gravity as we lifted it up? Do you remember that? And what do we use for the force of gravity? Do you remember? Yeah, mg, where g is 9.8. This takes us back to the beginning of the lecture. What did we say here about that equation? It's approximately true. And we will gladly use it as long as we're somewhere within the Earth's atmosphere. But what happens when you get too high? It's no longer valid anymore, right? So, just like we said, only use this formula when you are with, say, in the Earth's atmosphere. Because when you start to get above, then the extra height does matter. And I should add to that, use any formula or idea that is derived from it. This is a bigger philosophy that I hope you guys caught. But it's the easiest mistake to make. It's what students love to do. It's what I keep joking with you that I hope you will not do. Plug and chug. Ah, here's the equation. It was in the book. Teacher put it on the board. I'll memorize it. I'll plug it in. I'll get the answer. But if all you do is plug and chug, you can only do what problems have already been done before. In addition, you can make mistakes very easily by just saying, here's the formula I had before, but not knowing where it came from and why it came from runs into troubles, and this is an example of that. If I were just to sit back and say, I'm going to use the equation for the potential energy as mgy, not remembering that it came from here, I would probably plug in a height of 250 meters, and I would get the potential energy, and if I worked for NASA and tried to launch something, it would crash and burn and cost millions, if not billions of dollars, maybe even a loss of lives. And hopefully I would be fired for at least the sake of the rest of the humans in the world. You are just clueless. You didn't really learn what needs to be learned is to go beyond doing okay and getting an okay grade. And transferring to an okay school and working at an okay job for a while until you're fired and then going to the next okay job, right? There is something bigger in all of this, and that is my main point that I've said periodically and really shows up right here. What these ideas of science are built on and what the formulas are built on is important. The example I like to give, and I think I already have for this class, is if you wanted to install a pool on the top of an apartment building, does it really matter what the foundation is? I mean, we're not building the foundation. We're just putting the pool on this, up on the roof. I'm not even going to touch the foundation. I'm just going to tear off the roof and put the pool there. But does it matter? Yes, because eventually everything is supported by the foundation. And if you put a pool, and I pick on the pools because they got a lot of cement and a lot of water and they're very heavy, and if the foundation was not built to that strength, you can do all the things right on the roof and the whole thing just collapses because it is built on a support that doesn't have enough strength. And that's exactly what would happen here. If I were to come over here and just put this in, I would probably crash and burn. Whether I knew the reason why or not, I don't know if that really matters. These things unfortunately can happen. I'm thinking of a NASA event where one group of engineers were designing everything in the metric system and another group of engineers were designing everything in the English system. They merged their data, they launched the satellite. Actually, one group launched it and the other one transferred controls, and they obviously had information in wrong order of magnitude because one thought all the numbers were in feet and the other one thought they were all in centimeters, and what ended up happening is the whole $150 million satellite just plowed right into the surface of Mars. And so on the way to Mars it was supposed to turn, but nobody realized it was time to turn because their numbers were all wrong. And so all of this, what it is based upon, who's doing the work, is absolutely crucial. If you build a rocket booster and you assemble it together and you put O-rings between the rocket boosters, you need to remember that it is supported with rubber. And rubber is not flexible when it freezes. So if you wanted to make a seal, but it is 29 degrees Fahrenheit when you launch the rocket, it blows up and 7 people die and the whole space shuttle goes into disarray for dozens of years until we redesign the rocket boosters. You see my point? My point is each of these steps are very, very crucial. So that's a big philosophy, bigger than anything else I can say today. But let's apply that philosophy to this case. If this is what I do, I will mess up. So what am I going to do instead?
Integrate gravitation.
Yeah, I'm going to go back to my fundamentals and realize that we got this equation for potential energy by doing an integral of the force of gravity. So change it. We got a new equation for the force of gravity. So let's change it to the new equation and let's do the integral. And so we're going to end up with a new equation. So this equation is no longer going to be valid, although let me say it with a caveat. I would say it's still valid if we're not out of the Earth's atmosphere. But for the International Space Station, we clearly are out of there. So when I talk about the equation for the potential energy, I'll put new equation for the gravitational potential energy. And like we derived it last time, we will do it again by saying, let's do an integral of the force of gravity and then integrate as we go up. Now I'm going to change some symbolism here because when we did it last time, in fact maybe we should do a comparison here. I'll call this initial height, and we lift it up to a final height. And so we'll just kind of lift the baseball to a new height. When we did this back in Chapter 8, we were not looking at quite a big scale. We drew our Earth as flat. Then we said, okay, if this is the baseball at some initial height, and we lifted it up to some final height, we basically said that the force of gravity was a negative mg. Why negative?
Downward direction.
Yeah, and so that was the part we said back in Chapter 8 where we, in the derivation, are defining what direction is positive and negative. We didn't define where y equals to 0, but we did define which direction was positive and negative. And of course, when we were doing those problems in Chapter 8, we emphasized that. Of course, so now, then when I go up, I would go in the y direction. And so what we got, I guess I did not complete my equation correctly. There was a negative in front. And that's important to cancel with that negative. Because the potential energy, we said, was the opposite of the work. So work was just the integral. The potential energy was the negative of that. All right, so be careful with that. So my two negatives, the point is we would then have mg, and then we would have the final position minus the initial position. And so that's why we said the final potential energy was mgy final, and the initial potential energy is mgy initial. So again, just taking this as a little chance to review as we are getting ready for the final exam. That was the equation. It's going to change now because no longer is the force of gravity going to be a constant. And so that means when I come over to here, and let me put my negative back in here, then I would have the integral, and in place of negative mg, let's play the same game. Let's first of all put the equation for the force. So there's the magnitude of the force. What direction is the force? So in chapter 8, we put a minus because we said the direction was down. What would I do in this picture? And I guess the force is still down? Although I don't know if down is such a good word, because what if the ball was over here? What direction is the force of gravity? Kind of sideways?
Do you like clockwise, counterclockwise?
I'll take anything that works. I don't think clockwise or counterclockwise works. What direction would you call this force? Yeah, I'd call it radially inward, towards the center, right? So maybe what I should do then is say that it is going to be moving in a radial direction outward, and the force is radially inward. So see the slight change in the thinking process? I changed it from a y, moving the ball upward in a y direction, to saying I am going to be moving the ball outward in a radial direction, and the force of gravity is opposite of the radial direction. Fair enough? And so other than having an r instead of a y, and other than having that equation instead of the mg, I'm doing everything the same. The logic is the same. The equation is different, which of course means when I integrate it, I'm going to have a different equation. And in fact, maybe I should then put initial position and final position. I guess I did not put it on the limits of my integral here. I kind of indicated it after I did the integral. But since as long as we're reviewing, maybe I should be more clear that when we did this in chapter 8, we said let's start at some initial position and integrate to some final position. And so that's what I meant here. Start at some initial and go to some final. So it was y final minus y initial. So same thing here. I'm going to have some initial, but let me label it as an r, since we could go out in any of the radial directions, and an r there. And you can see I'm taking a little bit of extra time here because I think this is probably the biggest consequence. Remember I said at the beginning, I will not do anything in this chapter that is not just F equals G m1 m2 over r squared. But I think the ones we've done so far were pretty straightforward. We just took the force, we said took it to a circular motion. That was, I think, pretty straightforward. This one is a bit more complicated because we've got to go all the way back to the fundamentals and redo the integral. And so we are going to get an equation that's going to look very different than this. And that's what I'm trying to illustrate by taking my time going through this. So now let's actually do the integral. Because the integral itself, I don't think it's hard. I think all of you can do the integral. But I want you to realize why you should know that you were supposed to redo the integral. In this case, the two negatives will cancel out. That's good. The g and the two masses are a constant, so they can be pulled out of the integral. And what is the integral then of 1 over r squared? And don't forget the negative. Yeah. It's negative 1 over r, right? Maybe we should integral of r to the negative 2 dr, right? You add 1 to the exponent, and then you divide by the new exponent is how you do an integral of a polynomial, right? Add 1 to the exponent, divide by the new exponent. Which, when simplified, becomes a negative 1 in the top and an r in the bottom. So this is from some initial to some final. And so when I write this out, I get G m1 times m2 over a negative r final minus a negative G m1 m2 over r initial. And so again, the logic is still the same, but you can see that the equation I get over there is very much different than what I got before. And in fact, the equation then, maybe I'll put it over here and put a box around it, because as I get to this question, what is the gravitational potential energy of this International Space Station, then I need to use the appropriate formula. And so I would say our new formula can be generalized like that. Just like our old formula was generalized as mgy, this is our new one. Did you notice the minus sign in front? So not only is this a new formula, but I think it's easy to miss some of the important ideas here. There's two, I think, tough ones that showed up in this derivation that didn't show up when we did it in Chapter 8. For example, back here in Chapter 8, when we did this derivation, of course it was an easier integral because it was a constant, but did you notice then that during the derivation we called down negative, but we did not choose any part of this where y equals to 0. Fair enough? And so for the last, boy, how long have we been in classes here? 14 weeks? Well, we haven't been doing, but from 8 to, so last 6 to 7 weeks where we've been doing potential energy, you have heard me say again and again and again, if you use this equation, you can pick y equals to 0 anywhere you want. The thing you have to remember, though, is you have to use down as negative. And this is why. Fair enough? Let's come over here in this derivation. In this derivation, right here in this step, didn't I call inward negative? All right, so if we're going to use this new equation, then outward is measured in positive values, and what is inward? Negative. So that's pretty much the same. However, by using this equation, did we choose where r equals 0? We did, didn't we? And to me, that's one of two major differences to what we have been doing and what we are going to do. You see, in this derivation, we never picked where y equals to 0. So we had that freedom to pick it. But right here, when we put the force in, how do you measure r in the force? From where to where? From the center of the Earth out to this International Space Station. And so my point is, you no longer have the freedom to pick r equals 0 where you want it. It's been chosen for you. So, use this equation. Great equation. But please remember where it came from. When you build that swimming pool on the rooftop, remember what's underneath. Please, you will destroy something if you are not careful. Same thing here. Use this equation. Remember what's underneath it. And what is underneath it is inward is called negative. That's pretty obvious. But where does r equal 0? At the center of the Earth. Or if we were doing this for the sun, it would be the center of the sun. Did you catch that? You no longer have that choice. And I think because we have, for the last 8 weeks, have been saying you can pick y equal to 0 anywhere you want, students ask, can I go ahead and pick the 0 anywhere I want on that one? And the answer is no. Forget the International Space Station for a moment. Let's just ask, what is my gravitational potential energy? Here I am on the Earth. And when I say on the Earth, I'm on the surface of the Earth. So if I were to calculate what is the gravitational potential energy that I have, what would I do? Well, here's the equation. It's a negative. I'll put in the g, which is 6.67 times 10 to the negative 11. I will put in the mass of the Earth, 5.98 times 10 to the 24. I'll put in my mass, which is a little too high, but nonetheless, that's what it is. All right. 75 kilograms. What is my distance?
Positive number.
Can I put 0 here because I'm on the surface of the Earth? No. In fact, that would really be annoying if I did try to put 0 there, because then I would have a 0 in the denominator. And so what must I use for r? Yeah, the radius of the Earth. So 6.37 million meters. And maybe I should be careful with my units. This is a kilogram, this is a Newton, and then a meter squared over kilogram squared. So that the kilogram squared would cancel off, one of the meters would cancel off, you would get Newton times meter, and not a surprise then, you would get a unit of joule, as you should, since we are talking about how much potential energy do I have. And if I put that number into my calculator, starting with the minus sign, 6.67 times 10 to the negative 11, times 5.98 times 10 to the 24, times the 75, divided by the 6.37 million meters, I get a potential energy of negative 4.69, and I'll just do one more decimal, 0.696 times 10 to the, oh my gosh, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 joules. And again, it looks different. One of the obvious things that looks different is it's both a negative and a big number. But there's nothing I can do about that. If I'm going to use this formula, I have to stick to the guidelines of what that formula is saying. I said this back in chapter 8. Anything wrong with negative potential energies? No? We had that back here, or at least we could have, right? If you had a ball that started up here, and then you called y equals to 0 right here, then as the ball got lower, isn't its position negative y? And so don't you get then negative potential energies? So nothing is wrong with negative potential energies, although I must say we haven't used them very much, and it may look bothersome to you. I won't have time today to convince you the negative potential energy is actually going to be a big help for us. But we have yet to see that. But I think the first thing I want to point out is just this fact that it is a negative number. Now don't let that confuse you, because let's say that I went up to the International Space Station. What would be my potential energy there? Well, I guess I would still have a negative. And the constant, the universal gravitational constant, would still be the same. The Earth's mass would still be the same. My mass would still be the same. What has changed is I am no longer on the surface of the Earth, but I have gone up to however many meters this is. We never did calculate it separately, but that is how high I would now be. And so coming back to the negative 6.67 times 10 to the negative 11, and then the 5.98 times 10 to the 24 times the 75, then divided by, and I got to add these together, 6.37 million meters plus 250 times 1,609. I get a number of negative 4.417, and I bet that is billion. 123, 123, 123 potential. Again, notice it's still negative. But let me ask you this. Did my potential energy increase or decrease?
Increased.
Hmm?
Increased.
It increased, right? Isn't it less negative? So again, let me emphasize. Working with the negative, I have discovered in the past, has given the students the most troubles. Of any part of this chapter, it is the potential energy. And you can see why I'm spending the most time there. Is because it is a totally different looking formula. And when we write it out, we need to remember then that we must pick r equals to 0 in the center. That was the condition when we put in this equation. And so when we put it in there, and because of the integral, we get this minus sign. And I think the minus sign bothers people because we didn't have the minus sign before. Well, we didn't have the same formula before. So the integral was different. Duh, of course there's a different equation. It's a different integral. It's a different equation to begin with. And the negative sign seems a little bothersome, and that's why I wanted to make sure I took a little time today and then more on Monday to say there's nothing wrong with the negative sign other than it is different. And so a ball that would be going from here up to here would go from a negative energy to a less negative energy. Nothing wrong with negative potential energies. And that's what's happening in this equation. That's what's happening with my International Space Station. I have a negative potential energy, and I go up to the International Space Station. My potential energy increases. In fact, here's a fun one to ask. How high would I have to go until my potential energy is no longer negative? I mean, again, comparing to what we did back in chapter 8, you would have to lift this ball until you get to your definition of y equals to 0. Fair enough? At that point, your potential is 0, and anything higher goes positive. So looking at what I have to work with, how high do I have to lift myself until I have positive potential energy? Never, right? And so this equation is always negative. Now you may argue, what if I got infinitely far away? What would be my potential energy?
0.
0. See, that's why I could never get to positive. If I went higher and higher and higher, and if I went to the other side of the universe, what would be my potential energy now? 0. This is going to sound funny, but I want you to hear it. To leave the surface of the earth and to go to the other side of the universe requires a lot of energy. So much energy that it equals 0. Did you catch that? I'll say it again. If you were to go to the other side of the universe, how much energy do you have? 0. You have essentially increased from a negative, I'll call it a 5 billion, to 0. You have to give yourself 5 billion joules of energy to get all the way up to 0. That's a lot of energy. Now, it sounds funny that your total energy, at least potential, I'm not talking about kinetic again, we'll add that to it on Monday, but it's 0. And that is the important piece in this equation. It is always negative. And 0 represents an enormous amount of energy. It's the amount of energy you would need to break free from the planet. And it's going to become very useful. So as I promised, on Monday, you'll begin to appreciate the negative numbers. Because anything that is 0 or positive means you have enough energy to break free of the planet. Anything that is below 0 means you're stuck to the planet. So if I throw this up and it comes back down, what do I know? The total energy must have been under 0. It came back down. If I throw it so fast that it never comes back, what does that tell me?
Should start a career in baseball.
That I must have given it enough energy that it's greater than 0. Right? That's the idea. Well, more on this. We're out of time here for today. But you can see the consequence of this one is the most complicated of everything in this chapter. Just because it's a whole new formula with a negative in front and the 0 has to be measured from the center of the planet.